The example name is 1D Isothermal lithium-ion battery. To access the example files, we will go to the application gallery and we will search for the battery design model. And we are going to the 1D isothermal lithium-ion battery example. So we are going to download all the files first. These are the text files which we are going to need during the simulation. So I will save these files on the desktop so we can access them easily later on. Okay, now we'll have to download the PDF file. So this is the PDF file, and before going into the modeling instructions, I would advise you to first go through the introduction and the brief explanation about the problem or the example. Okay, and by the end of this example, we'll be able to generate these figures. So you will be able to have the discharge curve for various discharge rates, such as 0.1C, 1C, 2C, 4C, or you can make it or use different C rates as well. And you will also be able to do the cycling, or to be more specific, to do one cycle charge or discharge and then charge the battery again. Okay, so I'll leave all the other figures and we'll start with the modeling instructions. Okay, just to make it easier for you, I will have the PDF file ready and open the whole time at the right hand side, and the console window will be available and we'll work on it on the left hand side. So you'll be able to know the step I am in by looking at the PDF file and also noticing which page I am working on. Okay, so we'll start now the model instructions. So starting from the file or the new file here. Okay, so we'll start from the model wizard onward. So we'll select the model wizard and we'll go to the 1D, electrochemistry, batteries, lithium-ion battery. We will add that and we'll select the study, which is time dependent with initialization. We'll click done. Now we have reached to this point. Okay, so regarding the global definitions for the parameters, usually the first step when you are using CAMSOL is to load your parameters. These parameters are crucial for your simulation. Before the beginning of the simulation, it will give you an easy time through the whole process. So we're going to load the parameters, which is one of the text files which we downloaded earlier. So here we have the parameters. Okay, let me just go through a brief explanation about the parameters. Here the parameters are not variables. Okay, later on we'll come to the variables, but here are the parameters which we are going to use. These are known values we have, and here's the name of the parameter and here's the expression. Okay, there's a difference between the expression and the value. The expression is the number with the unit that you are going to provide CAMSOL with, and then CAMSOL is going to convert that into the SI unit system. So for example, instead of, let's say, 17.5 ampere per meter square, let's make it centimeter square. As you can see here, the units didn't change, but the value has already changed. So to change the value, you need to change the expression. And here's the description for that specific parameter. You can change the description in whatever you see fit. You can change the name, expression, or description. So this is for the parameter. And now the second step, we will go to the geometry. For the geometry, we will use the interval. This model is called P2D lithium-ion battery modeling. okay, or it is called Newman method. In this method, we can model the battery, we can model the electrochemistry part for the battery using one-dimensional simulation. And to do that, we are going to use the interval, and we are going to make sure that we are changing this one to be interval length. And we're going to write the length. Okay, after that, we'll click Build Selected. Okay, now as you can see here, in the graphics area, we can see that there is a line with 4 dots. On the left-hand side, we are starting from this dot to the second one. This one we have as the negative electrode, and here's the separator, and the last one is the positive electrode. So now moving to the global definitions in the example. Note the following. This model uses an interpolation function, which is imported from a text file for equilibrium potential of the negative electrode material. Okay, what does that mean exactly? You will be able to see that soon. Okay, so we are going to add interpolation function. This is not always needed. Only for this example, we are going to use that and we are going to follow it, but you need to do that later on. So to do that, we'll go to Home and we will add interpolation function in the global scale. And we will load the required information for the equation in this case. And we will change the label here to be. Then we'll go to the interpolation and extrapolation, and we are going to change this one and the extrapolation as well in this way. And lastly, we are remaining with the unit, which is volt in this case. Now we have reached to this step, and we're going to plot it. Now we have the same plot. Now the next step is that we are going to define a piecewise function which is going to be used to apply the current. And to do that, we'll go to the function piecewise, and this is going to be t, which is time, and we'll change the smoothing and the transition zone. And we'll load the cycle. And finally, the argument is going to be in seconds, and this one will be 1. And we will plot. So now we have this graph. Okay, so what does this mean is that, first of all, from the time 0 here until this time, we are going through the discharge phase. Then we are going to apply 0 current, so there will be no current flowing. Then we are going to charge the battery in this way from this specific time to this interval here. Then we are going back to the 0 state. Okay, so we are going to use this function to manipulate the current throughout the battery. Now we'll be working with the definitions. The definitions, we'll go to the variables. And for the label, this will be the positive current collector. And specify the positive current collector, we are going to specify it from here. Okay, so make sure you are clicking to the boundary. This is the positive electrode, and the one that's at the right hand side at the far end, that's the positive current collector. And if you want the negative current collector, it will be this one. But now we are only using the positive current collector. And we will enter the following for the variable. Okay, let me explain briefly what does this mean. Okay, this means we have a variable that's named app or applied current, and it is related to the piecewise function. And this piecewise function will be equal to 1 or -1 or 0 depending on the time interval which we just explained before. But this function is multiplied by the C rate. So from the parameters here, we already have the C rate, which is equal to 17.5 ampere per meter square. Okay, and this is the discharge current. So to be able to manage that, we're going to multiply it by the piecewise function. So in this case, we will have the required current at the specific time interval. Now we'll specify the materials for the battery. Okay, and to do that, we will go to the materials, add a material, and from the tree, we are going to select the one that's related to the positive electrode. So we are going to add the LMO material. Okay, we just added that. Okay, and for this one, since it has been applied for all domains, we are going only to keep it for the positive electrode in this case, which is the one at the right hand side. Now we'll go to the material, and we are going to check the equilibrium, and to be more specific, the interpolation one, and we will plot it. Actually, it is not required to do this step, but I'm not sure why it has been done here in this example, but I'm just trying to follow up the step-by-step instructions here. Otherwise, this step has nothing to do with the simulation. You can continue doing the whole simulation without plotting this interpolation function. Now we will add the electrolyte material. The electrolyte material, which is this one. We will add it to the component. And for this one, it will be for all domains. And now we will click to this node and the electrolyte conductivity, the interpolation, and we will plot it like this to produce the same graph in here. Now we will be moving to the physics, and to be more specific, into the lithium-ion battery physics here. And just to make it easier for you guys, let me just extend this one. And as you can see here, there is an X sign. We are going to deal with it later on. Or it just simply had been already removed because the electrolyte already covered all of the domains. Now for the lithium-ion battery, we are going to the physics tab, and we will add domains. So we are going to add porous electrode, and this one will be for domain number 1 because this is the negative electrode. Now let me explain briefly what's going on with this model. In this model, you will notice that there are many variables, okay, and they can be quite overwhelming. So this is the P2D model, and these variables, some of them can be found in the literature, while others are assumed, and others can also be calculated or measured experimentally. Okay, so to just make it easier for you guys, we are going to use whatever we have in the files for this example, and we are going to plug in the values of these input or parameters or variables. So I'll go quite quick in this section because I will need mainly to type in the name of the parameters which are available in the list of parameters. So we are done with this part, so we'll be moving to the particle intercalation. Now we'll be moving to the porous electrode reaction. Okay, as you can see here that the text color has changed to yellow, so that means there's a problem here. And it says that unknown function or operator. So most likely there's a problem with the function name. So this function is supposed to be the same as this function here. So, but here seems to be made a small mistake. This name shouldn't be only at the label, it should be the function name, like that. Okay, so now when we go back, we don't have any issue with this one. Okay, now we are done with the first one, which is the negative electrode. So now we will do it for the positive electrode. So we'll add a porous electrode for that one. Okay, now when you go to the electrode material, make sure you are selecting the LMO electrode. So this is the positive electrode in this case, because by default we have assigned the electrolyte material to all domains. So since this is a positive electrode, so we are going to specify it to be LMO. So for the negative electrode, what we have done here is that although it is specified for domain 1 and the material is used for electrolyte, but in the porous electrode reaction we're specifying that we are using this specific function, okay, for the equilibrium potential. So this function simply gives us the behavior of negative electrode, and this is most likely it's a graphite. Now going back to the positive electrode, so just make sure you are selecting the LMO electrode here. Now moving to the particle intercalation. Moving to the porous electrode reaction. Now the electrodes are ready, the negative and positive electrodes. So now we'll define the boundaries, and the first one is going to be the electric ground. And the electric ground will always be the negative current collector in this case. Now defining the second boundary, which is the electrode current density, which will be the positive current collector. And specify the current, this will be the variable which we defined previously. Now for the initial values, we're going to change this value to be CO0. We will save this file just in case anything happens. Okay, now we'll move to the global definitions, and in this case we are going to define the temperature which will be applied for the whole model. And now we are going to check the studies, and once we are done with the study, then we can compute the file. So going to the studies, we will define the time steps where we want the battery to run up to a specific time. So this is the output time, and that's going to be a range. So it will be from 0. We are going to change it until 8,000 seconds. It is in seconds. And the time step will be 10 seconds. And now we are ready, so we are going to compute this model. You can click into the log to see what's going on with your model. Now the simulation is done and we have the initial results. And now we need to do post-processing. So we will start by plotting figure number 5, which is this one, where we have the cell voltage and the applied current in the same figure. To create that figure, you can see that we already have part of it already plotted. Okay, and this has been already generated by default after the simulation of the cell. So to complete the plot, we are going to follow the instructions here, and we'll be doing the following. First of all, we will remove the title, which is this one. Then we will change the label to be cell voltage. And make sure you check the box of 2 axes, because one of them is going to be for the cell voltage and the other one will be for the applied current. And finally, we will go to the legends and we will select lower right. Now we will go to point graph number 1, which is specifically for the voltage, and we are going to show the legends. Okay, now you can see that we have the voltage and there's an arrow which indicate this line, which is the blue line, is specifically for the y-axis in the left hand side. Now to generate the current graph, we are going to duplicate the voltage one. And here, instead of having the voltage, we are going to change it to the current. Okay, and to get the current, so we'll go to the definitions, the variables, because we have already defined a variable that's called IAP, or the applied current, and we are going to select this variable. And to make sure the current is plotted in the right y-axis, in the right hand side of the y-axis, so make sure you check this box. And finally, we are going to modify the legends. Okay, so now we are done with this figure, and we'll be moving to the next one, which is figure number 6. This figure. To do that, we'll go to results, and we will add a 1D plot group. And from the data set, we're going to select none. And now we will right click and select line graph. From the time selection, we will select from the list and we are going to choose 10 seconds. So this means the plot is generated when the battery discharged for about 10 seconds. So we are not continuing that discharging. So only within the first 10 seconds. So we are just plotting this figure. And in this case, we are going to select all domains. And now we'll continue with the line graphs. Now we are going to edit the axis labels. And we will have the final plot in this case. Okay, so just let me remove the title to have it none, like that. Now we'll plot figure number 7, which is this one. Now we will select multiple times. So first I will select the 1200, then to select the 1800. Make sure you are still pressing the control key in this case, so you can select multiple times at the same time. And now we can edit the X and Y axis labels if needed. And then we'll move to line graph 1. In this case, we'll make sure all legends are shown. So when we go to the line graph 1, we'll click show legends in this case. And now we have this graph ready for us. Now we will plot figure number 8, which is this one. So we'll go to the results tab and we will add a 1D plot group. Now we'll be moving to the last figure, which is figure number 4, which is this one, which is about discharging the battery at different C rates. To plot the discharge curves, we will need to make some modifications to the simulation. Okay, so we will need to run the simulation again after doing some changes. And the first change that's going to be related to the current. But first of all, we'll need to add a parameter that's called C. And this parameter is the C rate. So later on, we are going to change this C to be 0.1 or 0.4 or 1 C rate. Also, we'll have to add a variable and we'll name it IABP. So this will be the current which we are going to use for the study, where we're going to show the discharge curves. The difference between these two currents is the following. As you can see, for the previous one, here we used the piecewise function in this case. Okay, and as you remember that the current is not constant, so it changes with time. But in this case, in this one, so we have the current, which is I1C, which is 17.5 ampere per meter square. That's going to be multiplied by the C rate. So the current will be constant. So we are going to have fixed state. That's going to be for the discharge one only. And now we will add an integration operator. And we'll specify the geometric interlevel to be the boundary, because we need to select the positive current collector to be able to get the cell voltage information during the simulation. Now we'll go to the physics or lithium-ion battery, and we are going to add another electrode current density that is specifically for the discharge curve case study. And we are going to use the new current. And just to be able to distinguish between the electrode current densities for the two studies, so we are only going to change the label for each one of them. Now we'll add a study. This study is specifically going to be for the different C rates. Now, to avoid one of the problems when we are using COMSOL, since we have electrode current density for study 1 and for study 2, which is for two different cases. So in this case, instead of having an error or a problem, so we are only going to use one of them for each study. So since now we're talking about study number 2, which is specified for the discharge curves, so we will only use this one. So we will disable the electrode current density 1. Okay, as you can see here, the electrode current density 1 is disabled specifically for study 2. Generally, it is still enabled. Okay, but if we are going to run only study number 2, it will assume that electrode current density 1 is not there. Okay, so now we can do the same thing. Let's say if we are going to run study number 1, we can just simply make the same modification and we can disable electrode current density 2. So there is going to be no conflict in this case. Okay, so you can run any of these studies separately without having any issue, and you can do any of the modifications here as well. Now going back here, we will add the parametric sweep. And now we will specify the variable which we want to change. Now note that the parameter value list is separated by a space here. So the parameter C, or the C rate, will be changing. The first value is going to be 0.1, and then the second one is going to be 1, and then 2, and the last one is going to be 4 in this case. After that, we need to specify a stop condition. So this is the stop expression, so I'll just explain it briefly. So what we have in this expression is the following. We have component number 1, which is this one, and we are telling consoles that for component number 1, we have the positive current collector, which is the information of the cell voltage which is collected through the simulation or during the simulation. And if this value is less than 2 volts, stop the simulation and you can move on to the next C rate. Now we have this study ready and we will compute. Now we are going to plot the discharge curves. Now note, because we have 2 studies, so in this case we'll need to specify the data set. So we are talking about study number 2, and to be more specific, for the parametric solutions. Now we have this figure, and as you can see that for 1C, 2C, and 4C rates, the lines seems to be behaving properly. But for the 0.1C, the line is incomplete. And what does this mean is that at 0.1C rate, the simulation didn't run for enough time to generate the full line. Okay, so this means there seems to be a problem with the time of the simulation. So we're going to check that, which is we're going to study number 2, and here's the output times. So what we entered here from 0 till 4,000 seconds. But if we check the example or the reference here, they're in the simulation for about 40,000 seconds. So we're missing 1 0. Still, even if we run the simulation now, we're going to have the same problem. So I will run it so for you guys to see the results. Then I'm going to fix the issue to know how to fix it properly. As you can see here, we have the same graph with the same problem. To fix the problem, although we have corrected the time to be 40,000, but still we need to also correct another one, which is, we have it here. This one, it is taking the previous value, which was 4,000. So this one should also be 40,000. So now we are going to run it again to fix the issue. As you can see here, the 0.1C rate is now fixed. So we have the complete line, so we can continue our work. Okay, so I'll go back till here. So now we'll change the title. And we'll modify the X and Y axis labels. And to clean the figure more, we are going to put the maximum and minimum limitation for each one of these axes. And we'll plot this one, and now we have the final figure in this way.